Good morning, everybody. My name is Andrea Trabattoni. I work at DESY in Hamburg, and my main research interest is the interrogation and possibly control of the photo-induced electron dynamics in matter. And today I would like to speak to you about a powerful spectroscopy provided by strong field lasers, that is laser-induced electron diffraction. And I'll try to give you an overview of the last advances. So let's do this. Let's start from the motivation. And here you can see I reported a small molecule, the OCS carbonyl sulfide molecule, let's say a friend of mine, where in red and blue, these lobes represent the charge distribution of one of the degenerate HOMO orbitals of the molecule. And I reported also the smaller bond length of this molecule, that is the OC bond, that has a length around, at rest at equilibrium, around 116 picometers. And we will learn in these days that if you want to really capture in real time the electronic motion and so the dynamics of the electron wave function, you really need attosecond resolution, because this is the natural time scale of electrons. But I would like to stress that if you want really to take snapshots of matter in action, temporal resolution may not be enough. You need also spatial resolution, really to do also imaging. And if we want to track in real time small changes of this bond lengths, we aim at having at least a few picometers spatial resolution. So if we want at the same time to observe in real time the electronic wave function and the structural dynamics, we need attosecond temporal resolution and picometer spatial resolution. So the take-home message is that we need an ultra-fast imaging technique. And before entering the details of the strong field option, that is laser-induced electron diffraction, I would like to show you what we have on the market. So the first option is a time-resolved X-ray diffraction. This is a kind of exploding really branch of research, really successful, and in the last, let's say, 10 years. And here I report what they did in this Nature paper in 2011. And the first name is Henry Chapman, who is a big name in this field now. And at that time, there were they wanted to image an extremely large molecule, so a protein, the photosystem 1. They were crystallizing the proteins in nanocrystals, and they were delivering into the interaction region here through a liquid jet, and they making the samples interacting with the X-ray pulses from the FEL at LCLS, where the parameters of the light source are the following. We have a photon energy of around 1.8 keV, so 7 Armstrong wavelengths, a photon flux of 10 to the 12 photons per pulse. At that time, a rather low repetition rate, around 30 Hertz. That means that they could acquire 1,800 patterns per minute. And the key point that the duration of the pulses were in the femtosecond regime. They were scanning between 10 and 200 femtoseconds. And this was good not only to guarantee temporal resolution, but also because if we give to the system, to the protein, such a huge amount of energy, you want to image the protein before it gets destroyed. So the femtosecond resolution was also really important to mitigate the damage and try to image the protein in the first instance of interaction. Good. With this method, here you can see, and thereafter the interaction, they were acquiring the scattering pattern, the Bragg peaks, on the large angles in the near field and on the small angle in the far field. And yeah, here you can see an example, a pattern, a low angle diffraction pattern with the Bragg peaks from this nano crystal. And the key point was, of course, summing a lot of diffraction patterns. Here you can see the result with the 15,000 crystal patterns. And if you have really sophisticated algorithms to retrieve the structure from this diffraction pattern, you can really investigate in real time the structure of huge systems as proteins. And the state of the art of time-resolved X-ray diffraction, you can have even sub-Armstrong spatial resolution, a temporal resolution, let's say in the order of tenths of femtoseconds. But the drawback is that, of course, the cross-section of rescattering scattering for photons is rather low. It's several orders of magnitude lower than electrons. And also for this reason, imaging light atoms in molecules such as hydrogen is extremely challenging. And the second option is ultrafast electron microscopy and diffraction. That means that you can have laser focus it on a photocathode, and in this way create a bunch of electrons. You create your own electron gun. You can shape and manipulate this bunch of electrons both in the spatial domain and in the temporal domain, and you can use them as a source to do diffraction. And these electrons usually have a huge energy from kevs even to the MeV energy range. At the state of the art, they also can have a good spatial resolution in the order of, anyway, sub-Armstrong. The temporal resolution can be really good, a few femtoseconds, or if you read some papers, even sub-femtosecond, but the price that you have to pay is that you have to reduce the number of electrons in your electron bunch, of course. But again, since the electrons are so energetic, it's still really difficult to image light atoms such as hydrogen. The third option comes with the strong field physics. In the prototypical strong field interaction, we learn also in this day, you have an ultra-intense laser pulse that can interact with your target. Here reported again the OCS molecule. And you know that a portion of the electron wave packet after tunneling ionization can simply leave the interaction region, and we call these electrons direct electrons. It are useful because you can do spectroscopy on these photoelectrons and learn something, for example, about the ionized or excited orbitals. And in general, you can do spectroscopy of the strong field ionization physics. But we also learned that, of course, portion of electron wave packet can be trapped by the electric field and redirected onto the parent ion. And through recombination, we can have the generation of high harmonics that are another powerful spectroscopical method to investigate the electron wave function, especially of the parent ion. But you can also, of course, generate attosecond pulses that are key to do spectroscopy with the sub-femtosecond resolution. But we have also a third channel, because part of the electron wave packet that is returning onto the parent ion can be rescattered. And the nice thing is that these electrons are further accelerated in the field, and they acquire energy. You can image all your electrons direct and rescattered onto a 2D detector. For example, in a velocity map imaging spectrometer, you can acquire the angular resolved momentum distribution of your photoelectrons. And these high energy electrons contain, through the rescattering, a coherent diffraction pattern of your target. So you can really do diffraction, and this process was called laser-induced electron diffraction. But also you can have interference between direct and rescattered electron, and you can have holography. I'll try to give you some hints about holography at the end of this lecture. And one of the advantages of this laser-induced electron diffraction with respect to the other methods I just mentioned is that the peak current that we have at the recollision instant is extremely high. In this paper by Paul Corkum and in the group of Paul Corkum, they estimated the current density of the returning electron to be almost 10 to the 11 amps per square centimeter. And this is due to the fact that the electron wave packet is extremely short, that is attosecond, and of course, with also a spatial extension that is extremely small. And this is the reason for which this technique allows for the investigation of dynamical structures with potentially attosecond resolution and picometer spatial resolution. And I reported this reference also because this estimation was done within a study of electron impact ionization. So the electrons, well, while they are returning, they can extract other electrons. And this is another extremely intriguing channel in this prototypical strong field interaction, but I don't have time to speak about it. But I really encourage the audience to go in the details also of this channel and look in literature. So in this perspective, today I will try to give you some basics about strong field electron rescattering, some fundamental concepts in order to do a laser-induced electron diffraction, a lead experiment. I would like to stress the key role of the molecular frame, and then I conclude with some perspectives. So let's start with some equations, the physics of a strong field electron rescattering. So in these days, we learned that in the prototypical strong field interaction, after tunneling ionization, the dynamics of the photoelectron at a good level of approximation can be modeled with classical mechanics, was showed really nicely in the presentation by Lou. Basically, the electric field, the external electric field acts on the photoelectron as a force. So it's easy to write down here in atomic units the Newton equation for the electron. And if we integrate the acceleration, we can easily derive the velocity here of our electron and the time-dependent position. So we really have the equation of motion. And in this framework, of course, it is comfortable and useful to define also the ponderomotive energy, that is the cycle average quivering energy of the free electron in the presence of the electromagnetic field. And from this equation, we can also estimate that the maximum kinetic energy of the direct electrons, that means of all the electrons, as I told you, that are leaving the interaction region without coming back to the parent ion, is closer to 2up. And this is really easy to find from this equation, because if, as usually done, we consider the initial velocity equal to 0 or really small, at infinite time, this is the vector potential. At time infinite, we can consider it to 0. So we have the dependence only on the vector potential here at the time of ionization. And at maximum, you can see here that while at the peak of the electric field, the vector potential, that is the blue line, is really small. If we approach this point, the node of electric field, the vector potential is quite high, the maximum value. Let's call it A0. And if we, at ionization, we are close to the maximum value, A0. If you calculate the energy from the momentum, you obtain 2up. But it is a cutoff, so it's a maximum energy, and you have a drop of the count of electrons, simply because it's really easy, because you are approaching a point of the electric field where the ionization rate is really small. So you have a cutoff at 2up for the direct electrons. But as I told you, there is a portion of the electron wave packet that can return onto the parent ion. And for rescattered electrons, we need a further equation, that is the constraint of recollision. So basically, we are requiring that the position of the electron at the time of rescattering or recollision, as you want to call it, is equal to 0. So it comes back to the origin. And if we combine this with the momentum at rescattering, we can estimate the famous maximum kinetic energy of the electron at recollision, that is around 3up. Then the electron can be rescattered, further accelerated by the external field as a function of the angle of the rescattering. Here you can see the velocity after rescattering, and then you can calculate the average kinetic energy of the electrons after rescattering, and you can try to maximize this equation. And in order to maximize it, you have to consider backscattered electron, so with the angle of rescattering that equal to pi. And you can see numerically that if the phase of ionization is around 14 degree and the phase of recollision is around 265 here, well, the maximum kinetic energy is around 10 times up. And these are the backscattered electrons, for which anyway you can see the blue curve. for these electrons, anyway, the ionization rate from time zero is remarkable. And for this reason, with a relatively large amount of electrons that reach this 10 UP, that is the final cutoff. And by summarizing what we obtain, if we go back to our laboratory, we have our detector with the angular resource momentum distribution of photoelectrons. We can integrate our electrons along the laser polarization axis, and we will obtain this distribution with a large amount of electrons at low energy, the cutoff at 2 UP for direct electrons, then all the rescattered electrons, and the second cutoff for rescattered electron around 10 UP. Good. So this is basically the physics of the rescattered electrons upon a strong field interaction. But at this step, we have no idea why this electron should contain any signature of diffraction. So let's proceed in our investigation, and let's try to write down some fundamental concepts in order to do a laser-induced electron diffraction experiment. So the history began in 1996 in this seminal paper by Suo, Van Draug, and Korkum. They were doing a really easy but clever thing. They were basically simulating the strong field ionization from atomic hydrogen, and they were computing the ATI photoelectrons. So the photoelectron that you collect from this photoionization in the strong field regime. And then they were repeating the simulation. Instead of using hydrogen, they were using H2, so molecular hydrogen, and with the internuclear distance around 20 atomic units. And what they were observing is that actually the photoelectrons distribution was different. So there was a signature that in the photoelectrons of the molecular nature of the target. But at this step, I mean, we cannot say we cannot say something really conclusive, because this could be due to the fact that the orbitals of H2 are slightly different. So what they did is take again H2, but now slightly perturbing the internuclear distance from 20 atomic units to 30 atomic units. And again, they observed that the photoelectrons were carrying a signature of this extension of the bond length. So they really concluded, okay, this method is nice, because within these photoelectrons, there is a signature of the molecular structure. They call this technique laser-induced electron diffraction as a promising tool to investigate molecular structure with an extremely high temporal resolution. And after this seminal work, there were a lot of outstanding results afterwards. I will pick up only a few. For example, I think this PRL paper from 2008 from the group of Koch, Gerhard Paulus, the theory was done by the group of Chidong-Ling, is particularly interesting. They were focusing on an atom, so xenon, rare gas atom, a simple system, not a molecule. But what they were doing doing again the strong field ionization of xenon with a few femtosecond pulse at that time at 800 nanometer, of course polarized along this direction. You can see from the symmetry of the photoelectrons that are rejected. And they were doing an intensity scaling, so from 410 to the 13 up to almost 10 to the 14. And they were investigating exactly the angular distribution of the high energy rescattered electron with the aim of observing some diffraction observable. And they plotted this distribution that you can see in blue line as a function of the intensity, and they were comparing with a well-known rescattering cross-section of xenon. I mean, scattering and diffraction formalism was already present from decades, and the scattering of atoms is quite well known. And they were observing anyway that cranking up with the intensity at the certain point where with the highest intensity around 10 to the 14, well, the experimental results, so the angular distribution of the photoelectrons were approaching quite well, and they were describing really the scattering from xenon, and they were capturing the shape of the atom in this way. So it was a good result. And they did the same also for other atoms, krypton and argon. So this was a quite interesting result. But the question at this point is why they needed to increase the intensity to really observe the shape of the target. And to understand this, we can do a step back and try to really understand what we need for lead to work. We can go back to our friend, to OCS molecule. We have our bond lengths around 116 picometers. And let's say in a really conservative way, we can consider that in order to solve these bond lengths, so to do diffraction, we need a spatial resolution around 100 picometers. That means that this needs to be the wavelengths, the de Broglie wavelengths of electrons that are returning on my molecule. And this means that the energy of these electrons needs to be around 150 electron volts. But you know that the maximum energy we just saw, that the maximum energy of electrons are related to the ponderomotive energy. And this means that through this relation, it means that the ponderomotive energy needs to be 50 eV, and it is proportional to the intensity and the square of the wavelengths. What they were doing with xenon was basically increasing the intensity until a value of UP that was giving the proper energy of the photoelectron that allowed them to observe the shape of the atom. This is good, but this is because they could access only an 800 nanometer laser. But you know, if you read the manual of the good strong field physicist, at page 2, there is written that if you want to increase the ponderomotive energy, you shouldn't play too much with intensity, because if the intensity is too high, you start to deplete your target, you start to have plasma, and your electrons at 10 to the 16 watt of a centimeter square starts to be relativistic and experience an helicoidal trajectory. So to be conservative, you should stay in the 10 to the 14 or 10 to the 15 and try to increase the wavelengths. If we stay really conservatively in a range of 10 to the 14 watts of a centimeter square for the intensity, in order to have 50 electron volt for the ponderomotive energy, we need a lambda to be around 2 micron. So the take-home message is that the first ingredient for lead to work is that we need infrared driving lasers to have the spatial resolution. But this is not the only ingredient. Here in this graph, you can see from this PRA paper, you can see how the scattering works for conventional electron diffraction and for lead. And you can see that here you have the impact parameter, that is basically the distance that you have from your bullet and your target. And if it is too large, the scattering doesn't work, it's not efficient. So you need to be in this region, and they analyze what is the scattering angle for the two methods. And you can see that the two methods really live into parallel universes. And this is due to the fact that, as I told you at the beginning, with the conventional electron diffraction, the kinetic energy is in the 100 kevs or even in the math. While for lead, we saw here that the typical kinetic energy is several order of magnitudes lower, so hundreds of electron volts. But for both methods, we have to accomplish a certain momentum transfer, so an energy exchange between the bullet, in this case, our electron wave packet, and the target, in order to get in the electrons imprinted the diffraction pattern of our molecule. And this is the definition of the momentum transfer Q that is depending on the momentum at rescattering and the rescattering angle. And this is becoming clear while they live in different universes. For conventional electron diffraction, you have an extremely high momentum, then you have an extremely small angle of rescattering. You are basically forward scattering. For lead, it is the other way around. You have a small energy at rescattering, and for this reason, you need to have larger scattering angles, possibly backscattered electrons that are the one we saw that provides also the largest energy. So combining these two constraints, the first ingredient for our experiment is that we need backscattered photoelectrons upon IR photoionization. Good. So we can go to the lab, take an IR laser, photoionize our molecule and acquire the photoelectrons. And we will measure something like this. This is a simulation, but anyway, this is a cut over an experimental a simulation of an experimental momentum distribution of photoelectrons in the laboratory frame, really on our detector. This D distribution as a function of the angle theta from the center of our detector and K, and the K vector. And from this point of view, how we can proceed. So we would like from this momentum distribution really to understand the scattering event and see what are the parameters for the rescattering. So we need that this distribution is a function of the variables of the scattering event. So the momentum of the electron at rescattering and the angle of rescattering. And actually, this relation is extremely easy. It is provided by quantitative rescattering theory. You can see all the details in this PRA paper by the group of Chidon-Ling, where they demonstrated that with a certain amount of approximation, we can factorize our experimental distribution of photoelectrons as a multiplication between the energy distribution of our electrons that are considered to be weakly dependent on the target and on the ionization process. So we are basically assuming that the electrons are returning on our parent ion molecule as a plane wave. And then we have the differential cross-section of scattering, that is the object that we need to analyze in order to retrieve the molecular structure. So it is our diffraction observable. And in this way, we can really do a change of basis, go from Ky and Kz in laboratory frame into the rescattering frame that is Kr and theta r. Here you have that along the laser polarization axis, that is Z, you have to consider that at the moment of rescattering, at the instant of rescattering, you have the vector potential of your laser field that is shifting the momentum of your electron. So actually the origin of my rescattering frame is not at the center, but here where this distance is the vector potential. And then from here you can draw the Kr, so the momentum at rescattering, and the angle of rescattering. These two equations are not completely satisfying, because you see that we have still a dependence on the vector potential of the laser field that we wouldn't want, because otherwise it's dependent on your external field, the diffraction that you get. But fortunately, in the strong field interaction, we have that the ratio between Kr and the vector potential is relatively flat. So we can replace this A0 with a fraction of again, of the momentum at rescattering, as with a good approximation, and finally having our good change of basis, so we can analyze our experimental distribution in the rescattering frame and build our differential cross-section of scattering. So good, well, now we can also analyze our data, but we are still missing where is the bond length of my molecule from this equation. This is not clear, or in this differential cross-section. The last ingredient is the independent atom model. Basically, we have this from quantitative rescattering theory, but the independent atom model that was applied again by the group of Chidon-Ling to the frame of laser-induced electron diffraction is telling us that the differential cross-section, that actually in general should be dependent also on the orientation of the molecule with respect to the K vector of the returning electron wave packet. And is the sum of the contribution is written as a sum of the scattering contribution from every atom of my molecule, where you have the atomic scattering amplitude, and here finally this phase term that contains the momentum transfer and the internuclear distance. Finally, we have our bond length. So here is the signature of our molecular structure. We can simplify this equation. You see that you are summing on all I and J, But for all the I equal to J, you have the self terms that are basically the incoherent sum of the scattering amplitude of the atoms. That is not what we are interested in. We are really interested in the molecular structure, so in the bond lengths, in the cross terms. So we have this incoherent sum plus this interference term. That is what we are interested in. And where I is different from J, we can call it I, the total signal. And usually people like to define the molecular contrast factor, this MCF, where from the total signal you subtract the incoherent atomic contribution and you normalize to it. And then here is the complete equation where you are integrating, so you are taking care also of the molecular orientation. And an important thing that I would like to stress is that, of course, that since here the phase term that is really telling you the bond length is containing the internal product between the momentum transfer of your electrons and the internuclear distance, you would like them to be parallel. So if here you can see this simulation done from the CO2 molecule, you can see that if they are parallel, if the angle is 0, the oscillation in the molecular contrast factor has a large contrast. And while if it is isotropic, the contrast is lowering. And if it is perpendicular, you are basically having a flat molecular contrast factor that is, let's say, jeopardizing the information about the molecular structure itself. Good. So I would say that now we have our recipe to perform the experiment and retrieve molecular structures. We can go to the lab. We need ultra-intense infrared driving lasers. We acquire our electrons. We analyze our electrons thanks to the quantitative rescattering theory, so we can extract the differential cross-section. And then we can interpret these differential cross-sections as with an independent atom model and write down these phase terms and really retrieve the bond lengths. That is the dynamical molecular structure. So this is the recipe, and the first experimental breakthrough using this full recipe was in 2012 in this Nature paper by the group of Ludi Mauro, where they do exactly what we explain now, and they were focusing on really small molecules, on N2 and O2. And here you can see exactly what we said. We have the experimental photoelectron distribution. They were shifting the frame from the laboratory to the rescattering. This is the momentum at rescattering. And they were acquiring and plotting and analyzing the momentum distribution of the high energy rescattered electrons. And the nice thing is that they were performing the experiment at different wavelengths. So where they were starting with 1.7 micron. And what's happening by scanning the wavelengths? By scanning the wavelengths of your driving field, you are doing a kind of pump probe experiment, because after photoionization, your electron travels in the field and it recollides at the certain time of rescattering that is depending. And the time lapse between ionization and rescattering is, of course, depending on the wavelengths of the trajectory of the electron. So let's say that at 1.7 micron, the electron wave packet is revisiting your molecular ion and doing diffraction after 4 femtosecond with respect to ionization. If you increase the wavelengths, instead of 4 femtosecond, you will have 5 femtosecond. And if you increase the wavelengths, this time lapse will be 6 femtosecond. And you are scanning the time between the ionization and the rescattering. And by using this trick, they were able really with an extremely high temporal resolution, and with the spatial resolution they stated around 5 picometers, they were able really to compute the dynamics of the molecular bond after photoionization. So the molecular bond of the ion, both for N2 and for O2. That's good. And this was an extremely important breakthrough for the first experimental application of laser-induced electron diffraction, and was followed by important results. I would like to mention the work performed in the group of Jens Biegert in 2015 and recently. And I would like to mention because they applied a quite an important technological, let's say, improvement. That first of all, they were using an OPCPA providing laser radiation at 3 micron with a high rep rate and 160 kilohertz. And for this reason, they had the possibility of performing the experiment in a reaction microscope. So we're acquiring in coincidence ions and electrons. And this was key really to cleaning your photoelectron distribution and basically analyzing not all the electrons, but the electrons that are really related to the parent ion. Because as I told you, you have other channels, you have electron impact ionization. So your photoelectron distribution may be dirty and contaminated by other channels. They did this, and they were able for the first time to solve not one bond as in the paper by the group of Ludi Mauro, but 2 bonds. So the CC and the CH bond, again with picometer resolution, and you can see sub-femtosecond resolution here. And in the same group, same methods, same experimental approach, they were also, let's say, imaging a prototypical chemical reaction. So the Coulomb explosion of C2H2 decation with the proton loss, with the hydrogen plus loss. And they were doing as a function of the molecular orientation with respect to the electric field. And when the electric field is parallel, the states of the decation are strongly dressed, and you basically enhance this proton loss. And you can see that from the experiment and comparison with the simulation, they were really able to see that one CH bond was indefinitely elongating, really suggesting this proton loss, while the other one on this side was basically remaining close to the equilibrium position. And with the perpendicular alignment, anyway, this was not happening because the dressing of the states by the external electric field was extremely moderate. Good. This was an important result published in Science in 2016. But now I would like to really focus on the key role of the molecular frame. And to understand what I mean, we can go back to our recipe. And as I told you, the seminal concept of quantitative rescattering theory is that the electron wave packet is basically the returning electron wave packet onto the molecular ion before rescattering can be assumed to be a plane wave. But this is a quite large approximation, and actually in the last years is becoming clear that in many cases we have a breakdown of this approximation. And the first hint came from this, I would say, really nice work by performed in Berlin by the group of Johann Mikosch. They were analyzing the strong field ionization and rescattering from butadiene molecule. And in particular, they were focusing on the photoionization from 2 channels, from these 2 orbitals, the D0 and the 1. Here you can see the computation of the outgoing electron wave packet that you can see is really different for the 2 orbitals. And this is due to the imprinting of the symmetry of the orbital in the outgoing wave packet. And this anyway was really known, this general concept from decades. But they were really able to experimentally probe the ionization probability, but also the rescattering probability. And you can see that due to the imprinting of the outgoing electron wave packet, also the rescattering wave packet as a function of the ionized orbital is different. Here for the D1, we have a peak at this molecular frame angle around 90. Instead, for the D0, we have a well. And this was supported by simulation. And this was evidently demonstrating that the returning electron wave packet is not a plane wave, but is depending on the molecular target itself. And so this question can be raised: what is the real interplay between the molecular target and the driving field in a self-diffraction experiment? So is the molecule important only to contribute to the self-diffraction of itself? And this is what we investigated in this work here at DESY. And this work was performed in the laboratory of Jochen Cooper. And what we did was taking again OCS and prepare a cold ensemble of molecules and align them adiabatically with an alignment laser and confine them to a small angle distribution with a cosine square into d equal to 0.9. The maximum is 1, so really confined, really well aligned. And we were alternatively aligning into different configuration, parallelly and or perpendicularly with respect to the polarization axis of the ionizing laser. That was a laser at 1.3 micron with an intensity around 10 to the 14 watts over centimeter square. And in that case, the Ponder motive energy was rather low, but we were not interested to solve the structure of OCS, but really studying the properties of the returning electron wave packet as a function of the ionization and the molecular orientation. And already here, yeah, you can see what we did. Of course, we did the experiment in a velocity map imaging spectrometer that allowed us to acquire the angle resolve momentum distribution of our electrons in the two cases. And besides, you see some difference at low energy. It's evident that if we focus on the backscattered electrons at high energy, the electron that we expect to be at 10 UP, you can see that while for parallel alignment, we have that the maximum momentum is around 2.5 atomic units. It is larger for perpendicular alignment. So it seems that we have a different cutoff. And to corroborate this preliminary observation, we analyzed the data more carefully. And here you can see a close comparison between the momentum distribution for parallel alignment and for perpendicular alignment. And you can see that the momentum distribution at high energy is different. You can see here the distribution with a larger ratio of rescattered electrons also for perpendicular alignment, especially in the high energy region. And by plotting the distribution and calculating the cutoff as at the change slope in the distribution, you can see that while for perpendicular alignment, this was as expected by the classical model that I showed you at the beginning, it is at 10 UP, is strongly reduced in the case of parallel alignment. This was quite surprising. So we asked theoretical support and we collaborated with a group of Angel Rubio. They performed TDDFT calculations, time-dependent density functional theory calculations, and actually the result of the simulation is an excellent agreement with the experiment. Also in this case, you see that in the distribution, in the two distribution, where red is for perpendicular and blue again for parallel, as for the experiment, while for the perpendicular alignment, we have the expected cutoff at 10 UP, instead for 8 UP, for parallel alignment, the UP dropped to 8 UP. So what is the origin of this drop? And to try to understand what we did at the beginning, let's say, try to focus on the ionization step. So we focus on the low energy region where we have the direct electrons, and we did a differential analysis. So we took the distribution for parallel alignment, this one, and for perpendicular alignment, this one, and we subtract one from each other. And of course, in this difference, it means that positive signal means that we have a larger contribution for perpendicular alignment, for parallel alignment, and while negative contribution correspond to a larger contribution for perpendicular alignment. And this is the result from the experiment. We see that the larger contribution for parallel alignment here in red are these two lobes with a larger lateral momentum, transverse momentum, while along the laser polarization axis, that is the y-axis, we have a depletion. That means that we have a larger contribution from perpendicular alignment. But this is quite understandable and also intuitive, because in the case of parallel alignment, even if we have a laser polarization that is aligned along the vertical axis, Anyway, the symmetry of the HOMO orbital from which we were ionizing is inducing an angle of ejection on the electron. So it makes the electron acquiring a lateral momentum and an angle of ejection. And this is the reason for which we have these lobes that have a larger transverse momentum. While for the case of perpendicular alignment, the symmetry of the HOMO is allowing the ejection along the laser polarization axis. And this was in excellent agreement with the TD-DFT calculations, and also with the semi-classical model developed by Jos Wiese from the group of Jochen Kupper, where the ionization was modeled with a well-known ADK theory, and then the trajectory of the electrons were simulated classically. So this is concerning the ionization, but what is the consequence on the rescattering? So to really have an idea of what's happening in the rescattering, we were using this semi-classical trajectory simulation, really to see the trajectory of the electron as a function of time. And we were plotting this graph, where basically this is the electric field. We were ionizing from the first portion of the electric field, and we were, as a function of time, we were computing the peaks of photoelectrons, the peaks of absolute momentum of the photoelectrons as a function of time. So if the electrons are ionized here, the first peak of a boost of electrons are at the first returning, where the electrons are returning here and then rescattered, and they can reach this 3 atomic unit absolute momentum that I remind to you is equivalent in energy to this expected 10 UP. But then the electrons can also miss the first revisit. They can revisit the parent ion later, because anyway they can pull back by the Coulomb potential of the molecule and revisit later, but they will have a lower energy, or even later, even later, and even later. And as an order of revisit order. The fact that you have a lower energy, final energy at later revisits is well known from decades, but actually what we surprisingly discovered is that if we repeat the same simulation now for parallel alignment, the picture is really different. The first revisit, that is the one that is always assumed in any laser-induced electron diffraction experiment to be the main contribution, and only that is analyzed. For parallel alignment, that is also the alignment for which we have more information about the structure, as I told you at the beginning. The first revisit is completely killed, and this is due to the angle of ejection of electron due to the molecular orbital. And then the electron can be pulled back in the vicinity of the molecule by the Coulomb potential of the molecule, revisited at the second revisit, and then also the third revisit. And the highest energy that you can reach, I mean, the first time that you can reach high energy is exactly at the third revisit, where the highest energy that you can reach is this 9 times UP, that is in good agreement with what we observed in the experiment. But this, I mean, from this we can really draw some important conclusion that actually the final photoelectron momentum is strongly affected by the initial angle of ejection and by the density of the electron in the molecular potential. Also, higher order revisits for this reason are important. And but also, due to this fact, a complex energy-time relation is encoded in the photoelectrons, because while in this case the electron is rescattering after less than 1 optical cycle, so at the first revisit, so let's say after 3 or 4 femtoseconds, here for parallel alignment the electron is rescattering much later. So the time that we assume, the time lapse that we assume as our elementary step to do lead experiments is not defined only by the laser, by the molecule itself. And this is important to take into account. And the take-home message is that, yes, laser-induced electron diffraction is is a powerful method and intrinsically is a time-resolved method, but the temporary solution may be different from what we expected so far because we have also to consider the interplay between the laser and the molecule. By taking into account this interplay, we could really improve our temporary solution and try to develop experimental protocols that are able to isolate single revisit orders and to have a clear idea about the delay between ionization and rescattering. That is our time resource measurement with a lead experiment. So I would like to conclude with a few perspectives with this method. And well, first of all, so far I described to you only single field lead. That means, of course, we have a temporary solution, but the temporary solution in the time-resolved fashion is the time lapse between photoionization and rescattering. And this is occurring half cycle, of course, with the fact that we should consider also the higher order revisits, but this is considering the photo interaction only with one field, that is the strong laser field. But actually, we would like also maybe to do a real pump probe experiment as described by Francesca yesterday. So in that case, you don't have only the delay between ionization and rescattering, but the pump probe delay, because you can excite the molecule, for example, with a UV laser in a certain excited state, and then probe with lead the dynamical structure of your molecule after this excitation. And this is still challenging, and several research groups are starting to do this type of experiments, but it's really in its infancy. And before concluding, I would like to provoke your interest on another channel that is anyway involving rescattered electrons. I will not go in the details because I don't have time, but I think that is particularly interesting. And that is the interference between direct and rescattered electrons. And if you focus on this photoelectron distribution, for example, it's quite blurred, but you can imagine that there is some structure. And in this region, you don't have only direct electrons, but you have also the interference between direct electron and rescattered electrons. And this interference is considered to be holographic features, where your direct electrons are the reference trajectory, and your rescattered one is your target trajectory. So that is the definition of a hologram. And what we can try to do is focus on this low energy region and apply some edge finding methods. Let's say we could try, for example, to calculate the 2D Laplacian of this low energy region and see what's appearing, what's happening. And this is what I obtained. And that is quite intriguing. And you see there is a rich amount of structures and interference terms, and that are known exactly to be the interference between direct and rescattered electrons. And traditionally, in the last 10 years, it was considered that these features are weakly dependent on the target. So it is difficult from these features to extract some information about the molecule and even maybe the dynamical molecular structure. But some last experiments and computations are demonstrating that maybe is not the case. Maybe we can really exploit these holographic features in a quite intriguing way to access information about the target. And I don't have time to explain anything about it, but I really encourage the audience of looking at this really nice and recent review about photoelectron holography. And with this, I would like to conclude. And I try to demonstrate to you that LEED is a powerful and promising spectroscopical tool to image molecular structure with a high temporary solution and high spatial resolution. It's a time-resolved method, but the time resolution requires a careful consideration of the molecular frame. And strong field-driven rescattered electrons may contain more information that was explored so far if we consider the photoelectron holography. And with this, I would like really to acknowledge the Attosecond group at DESY, led by Professor Francesca Callegari. I would like to thank all the group of Jochen Cooper, with which we performed the experiment on OCS molecule, on the molecular frame, especially Sebastian Trippel and the former PhD student Jos Wiese. I would like to acknowledge also the group of Angel Rubio for the theoretical support, and especially Umberto De Giovannini. And then I would like only concluding with a small window of advertisement, because at DESY I'm creating a new group with the aim of investigate a special family of electron dynamics that are the electron dynamics that are involved in the energy exchange between atomic nuclei and the electron shells during nuclear reactions in nuclear isotopes. It's a quite ambitious aim, but with a huge potential. I'm creating this new group, and I'm going to hire PhD students and postdoctoral researchers. If you are interested, even for curiosity, please don't hesitate to contact me. And with this, I really thank you for your attention.